Now let's get back to the design of the amplifier. Up till now we have considered various definitions of gain. These guide us during the design process, beginning with the selection of the transistor. We have talked about stability, both in-band stability and out-of-band stability, and we've talked about the desire of integrating the bias network into our matching network design. Shown on the top of this slide is the general architecture we want to use with a transistor. Perhaps the only thing we've left out is a feedback network that we could possibly use from the output of the transistor to the input of the transistor. At the bottom of this slide is the topology that we have in mind. All microwave design begins with some topology in mind. We don't simply synthesize it out of nothing. We always have some idea that's in mind. So what we have here is an inductor at the input L1. This will be a large inductor, and its purpose is to allow DC current, or DC voltage in this case, to be applied to the input of our field effect transistor. So L1 will have a large impedance at RF. It'll look like an open circuit, and L2 functions exactly the same way. C1 and C2 function to block DC current from flowing into the source resistance and the load resistance. And it would be wonderful if we could also include L1, C1, L2 and C2 into the matching networks, or at least as much as possible. We've considered many definitions for gain, and I'm sure it's fairly exhausting and fairly confusing. But what we have here on this slide are the main definitions of gain. Let's go through the gain definitions on the right here. G on its own is our power gain. G is going to be the ratio of the power that's actually delivered to the load to the power that's actually input to the transistor. GT is a more useful metric of gain because it is the power delivered to the load divided by the power that's available from our source. So GT is G with optimum M1. Now that is a real gain. GTU max, which is our maximum unilateral transducer gain, is GT, or G if you like, where we artificially set S12 equal to 0, but it is the gain with optimum M1 and M2. Perhaps S12 could be set to 0 using a feedback network that does not affect the other S parameters. But it is an artificial gain. It is used in guiding design, and GTU max is a good metric to use in selecting transistors. The GTU max gain is a good indication of the gain that we can achieve without too much trouble. Another gain, GMA, is the maximum available gain, and that is the gain with optimum M1 and M2. So it is a real gain as well, what we're going to actually get from our transistor without feedback. Of course, with feedback we could turn our amplifier into an oscillator and we would have infinite gain. GMS is another artificial gain. GMS is equal to GMA, the maximum available gain, but we artificially just set K to 1. And the concept behind this is that it'll give us an idea of the gain at the edge of stability. The final gain that we list here is U, the unilateral power gain. This is the maximum available gain, which is a real gain, and we artificially set S12 to 0. So U is the maximum available gain with S12 set to 0 and with optimum M1 and M2. So GT and GMA are the only gains that do not modify the device. All of the other gains that we're talking about here do something a little bit artificial. They require modification of the device parameters, or at least of the effective device S parameters. Now our aim is to design an amplifier at 8 GHz. And there are 4 gains that we can use to get some idea of what the design process will be like. The first gain is the maximum unilateral transducer gain. This is the gain that we can achieve without too much trouble. That's what experience tells us. We use GTU Max to help us select a transistor at the very first stage of design. The maximum available gain is the gain that we're very likely to achieve without using feedback when we have both optimum M1 and M2. The maximum stable gain is an artificial gain, which is GMA, where we just artificially set K to 1. But experience tells us that while GTU Max, here it's 13.6 dB, is the gain that we can easily achieve, the maximum stable gain is a gain that we can achieve without too much trouble. So going from 13.6 dB to 18.2 dB is an increasing gain of about 4.5 dB, and we can achieve that without too much trouble. It takes a little bit of effort, but it's a gain that we can achieve. And the unilateral gain, 17.9 dB, is another gain which is an indication of what we can achieve. So what we've learned from this is that 13.6 dB is a gain that we can achieve without too much trouble. The maximum available power gain that we can achieve with our transistor is 14 dB, that's without feedback. If we did use feedback, we could easily, shouldn't say easily, but we can get to 18 dB without too much trouble. And the unilateral gain is also giving us an indication of the gain that we can achieve without too much trouble. Now we can design an amplifier to have a particular gain as long as it's less than the maximum available gain. So what are shown here are what are called the gain circles, and these gain circles, we can design our amplifier to have a particular gain. What is shown on this screen are the gain circles plotted on the gamma S plane. This is the gain with optimum M2, that is with the optimum output matching network. Shown in the center here is the maximum available gain. This is the gain with optimum M1 and M2, and this is 13.96 dB. In the previous table we said it was 14.0 dB. So the gamma S that we need to achieve this gain is going to be the gamma S corresponding to that point on the Smith chart. If we offset gamma S, let's say we picked gamma S to be out here, in fact anywhere on this circle, if we pick gamma S to be anywhere on this circle, the gain of our amplifier will be 12.96 dB. So we can design for a specific gain if we want to by deliberately introducing a mismatch. Now gain nearly always commences with the output matching network. We cannot design the input and output matching networks simultaneously. We don't know how to do that. The first process is to choose an output matching network that will provide the appropriate impedances to ensure stability below 5 GHz and above 11 GHz in this case. So between 5 and 11 GHz our amplifier will be unconditionally stable. Below 5 GHz it will only be conditionally stable, and between 12 and 21 GHz it will only be conditionally stable. So to design the matching network we must consider the stability circles. So there are two types of stability circles. There are the output stability circles, and they're the ones we must consider when we're designing the output matching network. So these are the output stability circles plotted on the gamma L plane. Recall that gamma L is the reflection coefficient looking into the output matching network from our active device. 8 GHz is our target design frequency. The shaded region encompasses the entire Smith chart, and that is telling us it does not matter what gamma L is, our amplifier will be stable at 8 GHz. It is unconditionally stable. But at 1 GHz some care is required. We must make sure that gamma L is in this region, in the shaded region. So if we chose gamma L to be capacitive at low frequencies, then we would ensure stability. If we chose it to be a short circuit, it would be stable as well. We must approach the short circuit point from the right direction. And if we just had a pure resistance, in fact the pure resistance is anywhere along this line, we would have a stable amplifier. At high frequencies, again we must be in the shaded region, and in this case having a nice 50 ohm resistance would ensure stability. So too would an open circuit. But a short circuit would surely result in instability. So let's add some numbers to the design of the output matching network. First thing we need to do is to calculate the impedance looking into the output of the transistor. This is Z out. We have a little problem here in that we have not designed the input matching network yet, and so we have no choice but to ignore S12 at this stage. But it is better to ignore S12 when we're trying to develop Z out than to ignore S21 when we're trying to develop the input impedance of our active device, which is what we'd have to do if we were designing the input matching network. Here we're designing the output matching network. Z out, when we do the calculation, Z0 times 1 plus gamma out over 1 minus gamma out. We're ignoring S12, so gamma out is just S22, and Z out comes out as 36 ohms minus J 27 ohms. So it looks capacitive with a resistance. However, the output of the transistor really looks like a resistor in parallel with a capacitor. And so we need to use Y out when we're coming up with the network that we want to match. Y out is 1 over Z out. It looks like a 56 ohm resistor in parallel with a capacitor. And this is one of the networks that we can use. Our source resistance is greater than our load resistance. Our source resistance is 56.99 ohms. It's greater than our load resistance. So let's look at candidate networks. Now we could have two versions of this output matching network. We could swap the inductor and capacitor around. Well, it turns out that this is a good choice. This is the better choice than the other, a dual circuit. So let's look at what happens when we are at low frequencies. Gamma L is the reflection coefficient looking into the output matching network, and the stability circles are gamma L planes that are output stability circles. So let's look at what happens at low frequencies. At low frequencies, this inductor will look like a short circuit. It'll become a short circuit. So we're in this region. That's where we're going to end up. That's a nice stable region. 8 gigahertz, well, we don't really care as far as stability is concerned. At 16 gigahertz, what's going to happen? Well, this is going to look like an open circuit. The capacitor looks like a short circuit at high frequencies, and so we see this load. And so we're going to be around this region at 16 gigahertz, and that's exactly where we want to be. We have a nice stable situation. So consider the dual circuit and what is going to happen. At low frequencies, again, this is gamma L looking into here. At low frequencies, what's going to happen is that we're going to see a short circuit looking through the inductor, and so our transistor will just see RL, and that will be stable as well. We'll be in this region. 8 gigahertz, well, we skip over that. At 16 gigahertz, look at what's going to happen. At 16 gigahertz, we're at twice our design frequency of 8 gigahertz. This capacitor is going to tend to be a short circuit. L will go to be an open circuit. Before we become a short circuit, we will be capacitive, and we will be in this region. So this matching network choice is almost certainly going to be unstable. Almost certainly will be unstable. So let's quickly go through our output matching network design. Here is our output matching network. There's our model for the output of our transistor, and here's our load. Our choice is to resonate out this capacitor, but we're using this matching network So XX, or I should say minus XX, will be included in our inductor. Ignoring XX and just considering matching RS to RL, this is our matching network design. We come up with RS. Well, we don't come up with RS. RS is 56.99 ohms. XP comes out as 152.4 ohms, and our capacitor comes out as some other value. We combine XP with XX, and eventually this is our final matching network design, which matches the active device, the complex impedance of the active device, to our load resistance. Let's switch over to considering the input matching network. Now we do know what our output matching network is going to be, so we do know what is terminating our active device, so we don't need to ignore S12 or S21. We calculate our input impedance as about 16 ohm plus J 17 ohms. So this is an inductor, and this inductance is coming from the bond wire, because this is a packaged transistor. There will be inductance looking into it, and so the appropriate choice for a matching network is as shown there. Again, this matching network must be stable, so let's do a quick check on what gamma S is. We're looking into the input matching network from our active device. At low frequencies, this capacitor will be an open circuit, so we're going to be in this region. At 8 gigahertz, well, we don't really care what's going on. At 16 gigahertz, the capacitor will be a short circuit. This will tend to be an open circuit. We'll just see this resistance RS, and we'll be in this region. So this matching network will result in outer band stability, and of course this is going to be a stable amplifier in band. It is unconditionally stable, so it doesn't matter what we do with our input matching network design. So running through the design, we're trying to match our active device, which has a complex impedance. This is our matching network choice. These are the stages in the matching network design. We should be able to resonate out the inductance looking into the active device. That will result in a capacitance, which will be just combined with the capacitance that we calculate in a purely resistive design of the input matching network. And finally, there's our last and final input matching network design. So this is our final amplifier schematic. So now we can see what we are able to achieve in terms of integrating the bias network. Well, L2 and C2, the values of L2 and C2 are just the values that came from our output matching network design, and fortunately we're able to use these elements as part of our bias circuit as well. In our matching network design, we had L2 connected to ground. It went from the output active device to ground, but VDD is effectively RF ground anyway. And so lo and behold, as far as the output network is concerned, we're able to incorporate the bias network in with the matching network. And so L2 is 1 nanohenry. It does not need to be a large RF choke inductance value. We were not so lucky with the input matching network. We still need to retain L3 and C3 as our bias elements. We'll choose L3 to be a large value of inductance, and by large value in a 50 ohm system we would be looking for a reactance of about 500 ohms, and so 10 nanohenry is a good choice for that. And for the capacitor C3, we would like that to look like a short circuit at 8 gigahertz, and 100 picofarads is a good choice there. That results in about a 5 ohm impedance. Now we designed the output matching network first, ignoring the input matching network, because of course we hadn't designed it yet. When we designed the input matching network, we were able to incorporate the output matching network. Now when we simulate this transistor amplifier, we obtain a transducer gain of 13.2 dB. This compares to the maximum available gain of 13.96 dB. The discrepancy is because of the assumption we had to make in the design of the output matching network. That is, we just took S12 equal to 0 because we had no choice. If we want to be more accurate, we could go through another stage of design. We could come up with a better estimate for the output impedance of our active device and redesign the output matching network, and we would get to 13.96 dB. Let's go back and revisit the design for a specific gain at 8 GHz. So recall that our simulated gain is 13.2 dB given that input and output matching network design that we did before. Here are our gain circles plotted on the gamma S plane. This is with the optimum output matching network. Shown as a single point is our maximum available gain, which is 13.96 dB. So we need gamma S to be at this point for maximum available gain. If we detune the input matching network, we can pick gamma S to be anywhere on this circle if we want 1 dB less gain, or we could pick any other gain we want. We can detune gamma S. So sometimes it is better to detune the input matching network so that we get maximum power transfer at the output of the device, so all of the power produced by the transistor is delivered to the load. But sometimes, especially if we're concerned about noise, we may prefer to detune the output network. But that's how we get a control gain, is that we detune the network. So let's summarize what we've been able to achieve. Here is our final amplifier. This is a surprisingly simple circuit. We had a well-organized design process to get here. We looked at various definitions of gain to guide us during the design process, but because we were going for maximum gain that could be achieved, we only used one gain, and that was GTU max, and we used that to help us select the transistor. Again, this is a surprisingly simple circuit that achieves both in-band and out-of-band stability, and as far as the matching network goes at the output, we were able to incorporate the bias circuit within that matching network